the example, I was planning to use the same PPT just to show that. So once we are done with that, otherwise it will be in a separate PPT. It will be one, the algorithm, and the example will be in another PPT. That is why I have actually not thought of sharing it today. So I hope my screen is visible to all of you. Yes.
Yes, ma'am.
Okay.
You can make it full screen. Yeah.
Sure. So what covered is, okay, let me just cover, I guess. Yes. So yesterday we covered a few basics of quantum algorithms mostly, and the no cloning, the math of no cloning and measurement. Post that, we have started with the quantum algorithm paradigms. We covered 5 different types of it, namely the quantum Fourier transform, amplitude amplification, and then adiabatic simulation, as well as the quantum walk algorithms. Then we started, we also have cleared that there are a few primitive quantum algorithms which are very fundamental for us to know, and just to understand how the oracle is developed, or how the superposed state are created, or how a particular state which you want as an output after measurement can be encoded into the can be encoded as one of the superposed state within that register. So just to understand all these things, it is very important. And then actually you are covered with all these like Deutsch Jotza, and the Bernstein-Wasserstein. And also I guess you were told the problem statement of Simons as well. And then yesterday we covered the Bernstein-Wasserstein basics and the mathematical expansion and all with respect to the generic terms. Okay, for the n-qubit ones. So I have told you that today, or so for next class, we will be starting with the example of that. So, and what was the problem statement for Bernstein-Wasserstein? That we have to search, our oracle function is such that we have to search a secret string. We have to search the secret string out of that superposed state. So let us assume that our number of qubits, say number of qubits, and also just to tell you, this is a continuation of just after that example. Okay, and this is you can find this example in the lecture, like yesterday's lecture content. So number of qubits is say 3. That means you can maximum input all these states, 0 0 0, and then 0 1 0, 0 1 1, likewise till 1 1 1. That is your 0 to 7. Right? Now, on application of Hadamard, when it is applied on QT-00, how we can do that? It simply means this, and this, and they are initialized with 0. So by doing this thing, equivalently, you can combine it and write it in this way. So on application of Hadamard on the state 0 0 0, what you will be getting is, we'll be getting some amplitude, which is nothing but 1 over root over of 8, and then all of these states, right? State 0 0 0 1, likewise till you will be getting 1 1 1, which you can also write in this way, all are ones, like 8 ones in a column vector. They are equivalent. So say our secret string that we wanted to find is, say, S, which is equals to, what should I take? Let me just take, say, 0 1 1. That is 3. We want to find 3. Okay, so that means we have to design the oracle in such a way that whatever I give as a secret string, ultimately that will emerge out as the measurement outcome. So what was the generic function for oracle? The oracle UF is defined such that your kx will be mapped to the output function -1 to the power s into x. What was s into x? It was a bitwise XOR, right? That is s1 x1 plus s2 x2 plus s3 x3 likewise till sn xn mod that 2, right? So similarly here also it will be exactly same. Remember the generic formula is kx will be mapped to -1 to the power fx. Your fx can differ, or like Deutsch dot said was to find the constant or the balance function. Here it is to find the secret string. So an oracle definition differs by only the term minus, which is in the exponent of -1. That is fx times x. Okay, that was a generic form. So for Marston Vazirani, this is the case. Now we will interpret that what we mean by this. Okay, the expansion. From expansion, you will understand that how to encode in quantum setting. So that means your initial size 0 is nothing but 000, right? And psi 1 is something which you have got like after Hadamard. So this is your psi 1. All these things. Now after Hadamard, you have to apply the oracle. So your oracle, after application of oracle, your psi 2 or a quantum state, a time evolution, say instance 2 will be 1 by root over of 8 will be as it is, right? And what is your x? X is the superposed one, and s is your secret string as per the notations here. See, this is s, and this x is the superposed one. So x actually holds everything 000, 001, 010, all the states, even including the 011. Okay, so x contains all these states starting from 000 to 111, and s holds only one state, that is the secret one, that is 01. So in that means, in that case, it is -1 to the power 000, that is x, in dot your s, which is 01. And what is the ket? Ket is x. Well, what is x? This is x. This is s. So it will be ket 000, right? And this is only for x equal to 000. So similarly, it will be for all the states. There shouldn't be any doubt to understand this. Then the next one will be 011.011. Then it's 011 plus -1 power 100.011. Get 100 plus -1 to the power 101, 011. Then get 101 plus -1 to the power 110, and then 011. Then get 110. And the last one is -1 to the power 111.011, then get 011. So this is the entire quantum state after the application of oracle. Okay, now let us understand that how we can compute this thing, right? So you will be taking any one, say I want to compute 111 and 01, that thing, just -1 power. So this is the power that you want to compute. So this is nothing but this 1 into 0, this is bitwise, then this, then this. That is 1 into 0 plus 1 into 1 plus 1 into 1 mod 2. That is, the answer can be either in form of 0 or 1. That is a modulo division 2. So this is nothing but this is 0, this is 1, 1. So this is 2 mod 2. And what is the remainder? What is the remainder here? It is 0. Right? Because 2 divides 2, that is the remainder is 0. Okay. So in that case, now let me take just one more. Say 101. What I want to tell, let me tell you. So it's a 0 into 1 plus 1 into 1. Have I written it right? 1 into 0 into 0 into 1 and then 1 into 1. 1 0 0 1 and 1 1. So let me take this thing mod 2. So this will be, I guess, 1 mod 2. So this is 1. So that means you can understand one thing, that all these factors, so therefore all of minus 1 to the power s into x will add nothing but some phases. So either it is plus 1 or it is 0, and minus 1 to the power 0 is 1, and minus 1 to the power 1 is minus 1. So it is adding either a 1 or a minus 1 with respect to the ket 0 0 0 till 1 1. So if you compute, the final output of psi 2 will be 1 by root over of 8, then ket 0 0 0 minus, this is 0 0 1, then is it minus 0 1 0 plus 0 1 1 plus 1 0 0 minus 1 0 1 minus 1 1 0 and plus 1 1 1. A few states will be having plus 1 and a few states will be having minus 1. So if I want to rewrite the corresponding expression, this expression, if I want to rewrite it, and why do we want to rewrite it, you will just be understanding that. So hold on for this one expression. If I want to rewrite it, rewriting the above expression, it will be 1 over root over of 8, then get 0 product 0 0, then 0 1, then minus 1 0 plus 1 1. Then it is basically, let me write a second bracket here, plus within second bracket get 1 tensor product 0 0 minus 0 1 minus 1 0 plus 1 1. The way we solve that quadratic equation. So this is the thing. Okay, let me just tell you how. Just remember, we are just taking out the zeros. Okay, nothing else. And also remember one thing, wherever you are taking, whether you are taking the first one or the second one or the third one, that respective position you should be like putting here. For example, if you are taking, say, this 0, okay, then you cannot take it at left. So it is like not in that way, it is not commutative. So you have to remember, A product tensor product B may not be equal to B tensor product A. So respectively, you have to take a common or rewrite it. Otherwise, it will be a complete error. So here, this is what we are doing. So that means we can write it in this way, that ket 0 plus ket 1, because this is the first output, right? So we cannot take the whole big expression as the first one. So this is ket 0 plus ket 1, and this one is again this thing 0 0 minus 0 1 plus 1. Now again we will rewrite it with respect to this one. So this is ket 0 plus ket 1. Okay, and this one is, see what we can take as common, this first 0 and the first one. Okay, so take this one and it will be ket 0 minus ket 1, and then it will be this minus 1, take this one as common, it will be ket 0 minus ket 1. Okay, So put it as it is, Ket0 plus Ket1 product. It will be again this. You cannot take this one as common first. So it will be this particular one and this one. So it will be Ket0 minus Ket1 and then a product of Ket0 minus Ket1. We are done. We are done with a few things, right? Our rewriting is over. Now, if you go back to the Bernstein Vazirani, what you are doing? Let me just go back to the oracle. So after all these things, what you are doing is you are applying a. This is what output we are getting. After this, we are getting the psi2, right? Then we have done nothing. We have not applied any gate. We have just done a simple algebraic simplifications. After that, what we are doing, we are applying a Hadamard on. No matter how many qubits you are applying an Hadamard. So now that means we have to apply Hadamard. Now, if you apply an Hadamard on all of these qubits, this is the first qubit, this is the second qubit, and you are applying an Hadamard, and this is the third qubit, and you are applying an Hadamard. So what will be the output? Hadamard of 0 is okay. Let me show you this thing. So that means on this particular thing, we are applying an Hadamard, right? So what is the Hadamard matrix? A 2 cross 2 Hadamard matrix. Or in short, let me write this means nothing but 1 and 1. Okay. And then Hadamard is nothing but 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. And this is nothing but 1 and 1. If you multiply it, what it will be? 1 by, and is it compatible? Yes. So output should be a 2 cross 1, this one and this one, because they are same. So we can do the matrix multiplication. So it will be 2 cross 1. So it's 1 by root 2 into 1 plus 1 by root 2 into 1. So that is 1 by root 2 into 1 plus 1 by root 2 into 1. And this is 1 by root 2 into 1 minus 1 by root 2 into 1. So it is obviously this thing. So this is what? This is nothing but this thing, right? What is the value? This is 2 into 1 by root 2. That is root 2. And what is this thing? This particular one is 0. So if you take root 2 as common, this is nothing but 1, 0. Now ignoring this amplitude part, what is the value that you are getting? You are getting that 1, 0. So what is the value of 1, 0? 1, 0 is nothing but your Ket0. Right? And similarly, if you do it with respect to the Hadamard of, say, Ket0 minus Ket1, and if I want to write, just let me write, because we are ignoring the amplitude. If I write it as 1, 1, 1 minus 1, and this one can be written as 1 and minus 1. Okay? This is the interpretation of Ket0 minus Ket1. So if you do that, it is 1 into 1 plus minus 1 into minus 1, which is 0. And this is 1 into 1 plus minus 1 into minus 1. Okay. So in that way, again, it will be some amplitude. Ignoring the amplitude, it will be 1. And which is nothing but your Ket1. So that means Hadamard, and this is your plus. We also call it plus. Your plus is nothing but Ket0 plus Ket1. And your minus is nothing but Ket0 minus Ket1. So if you apply Hadamard on plus, you will get Ket0 back. So Hadamard on Ket0 gives you Ket plus, and again Hadamard on that gives you Ket0 back. Because all quantum gates are reversible, so we are getting this kind of feeling. And Hadamard on Ket1 will give you Ket minus, and that on Hadamard will give you back Ket1. So that means if I go back, so this is nothing but Ket0, this is nothing but Ket1, and this is nothing but Ket1. So the final output is this thing into your and this thing will be adjusted here because we are getting the root 2 root 2 root 2, right? So in that way it will be basically this thing times, just check here, it was root 2, okay, and then get 0 product root 2 get 1 product root 2 get 1. So all the root 2's will be basically root 8 by root 8, which is nothing but 1, and get 0 1 and 1. So this is get 0 1 1, and if you remember, this was the secret string that we thought of obtain after measurement. So after measurement we obtain our secret string. Now what you can do it in home is you can basically take a 5 qubit register. A 5 will be I think more, so you can take a 4 qubit register, and then you just select the secret string as, so this is your homework, so 1010, and the same thing. So you have to design your oracle in that way and do all the computation, where your fx is nothing but, if this is s, so it's s into x, which is a bitwise basically XOR, and then you have to check that whether after measurement you are getting this 1010 or not. And just remember one thing here, x will be 1 over root over of 16, so which is 1 by 4. So it's always 1 by root over of number of states, maximum number of states that you can have. That is why for this one, we have taken this 1 by root 8, because 8 is the number of states that you can have if you have number of qubits as 3. Okay, so you can just check that whether you are getting this thing or not, and the state will look something like this, till 1111. And remember that 1010 will also be there within the superposed state. Okay, I think this is all of you have understood it. So let me just remove these things. Okay. So this completes your lecture 4. Let me take some question. Yes. No, of what you want to find, you have to know that. No, that has to be there with you. So that will be fed to your oracle. The thing is that you cannot do any such. You see, we are not hardwiring anything. Like we are not doing anything with the 011. Okay, because 011 is also there. My oracle has to feed, has to process all the inputs starting from 000 till 111, where one of the string as a hidden form, it will be there fed to the oracle also. Say there is an array, we want to do some searching, so definitely say it is a successful search, so 5 is there in the array, so maybe I have 1 3 4 5 9 13 2 0. So 5 has to be there, right? But your algorithm has to be written in a way that whenever it's a AI equals to item, it will return true, otherwise it will return a false. So this is a Bernstein-Vazirani algorithm that we are designing in this way. Yes. Yes, it is 1010. Get 1010. You can try that. Just check that whether after, and all of that, those things you have to do, the restructuring and all. Just check whether after that you are getting 1010 as the output of the oracle after measurement. So initially you have to start with 0000, then you have to apply Hadamard on all the 4 qubits, and after that there will be an oracle, so you have to write that oracle in that way so that the phase inversion and all those things happens. Okay, so any doubt in this example part? Yes, Oracle will be having the input S. So Oracle will be having everything, the S as well as the superposed one. And in the superposed, S is also hidden there. It's one of the element. S belongs to X. Yes, how to build Oracle? Yes. So are you asking that how to actually interpret the minus 1 to the power effects? That thing? I guess so. So for that, just see. Yes, I got that. So for that, you can please try it yourself. Please try it yourself that how and on what condition specifically. Basically, there will be S into X that you have to compute for all the states. Just take input as X and S both. Just write that function, Python function. Then just calculate it somewhere that for all the like 000 to 111, if it is decimal, then you have to break it. That is the logic. You have to break all the digits the way we used to break it and check that the way you converted it, right? So you have to first convert the decimal to binary. Then you have to take the bit by bit values and then do. I'm just telling. I'm not really showing anything. So just take the bitwise values and compute what is your S into X, which is that 1 into 1 plus 1 into 0. They are nothing till that, but there is no such quantum thing. So this will be our normal, simple, classical functions. So within that quantum program, it will be written that particular for loop and that particular S into X calculation. Right? Now, once that is done, whatever you are getting as value, based on that, based on that, I'm not writing anywhere. I'm just talking about it. Okay. Whatever value you are getting as the minus 1 to the power of S of X. So you just have to compute Sx. Okay. Here, there is nothing. So I'm not writing anything here. But whatever you are getting as S into X, that particular value, accordingly, you have to selectively add a phase gate. So it's a controlled phase gate, a CZ gate. Whenever you are getting some value 1, it will be minus 1 to the power 1, so it will be a phase inversion. So that means your, I will remove this part, okay? Or let me just write it here. Let me write it here. But this is under Oracle. This is under that Grover. What I'm telling is, just a minute. So first, what you can do is individually take the decimal values according to the like n value. You have to take the decimal, right? Then you just convert it to binary. You have to design it how you want to do it. Once you have converted to binary, then for n equals to 3, we'll be having all the combinations 000 to 111. And you have to write a for loop for that, right? For I equals to say 1, 2, number of whatever it is. So 2 to the power of that thing. Accordingly, you have to take, or say 0 to 2 to the power 3 minus 1. So 0 to 7, all of them you have to write a loop where you can convert it to binary. Once you have done that, just extract bits in binary. Then we'll be having all the bits, and then bit by bit do a bitwise XOR. Store it in somewhere. So A will be having all these values. So for 000.011, it will also be stored in A. And similarly, since there is a for loop till 011.011 as well as 111.011, all of these values will be stored in A. And within that itself, you have to compute the phase. What is the phase then? That means now minus 1 to the power A. How you can do that? For that, you have to feed your A as, say, X is that particular, all these values, 000 to 111. Right? That is your X cubed. right? Now this A is your control then. So it will be a control Z gate, so CZ gate of A and X. Now, after that, since you are doing all of these things in superposition, so all of them are in loop. So that means whenever your A is 1, your X will be plus X. Sorry, just reverse. Whenever A is 0, it will be plus X, and A is 1, your X will become minus X. Then you directly go to that one. So by what do you mean by this? That this means that after this entire thing, your oracle is designed. So after this, you have your oracle. So you will be standing somewhere. Oh, and I just missed this thing. So after getting this, you have to of course apply an head amount of X. That is definitely required. Head amount on X. And how you can do that? Head amount of say X0, head amount of X1, head amount of X2. Because X is nothing but your X0, X1, X2, which is your initial 000. Likewise, first you will be doing this, then you will be actually doing all these things. Then it's a control Z. Post that, you will be having your oracle ready, which is your kit side 2. After that, what you will be doing, you will be again doing 3 Hadamard on all the qubits X0, Hadamard on X1, and Hadamard on X2. Sorry, just a minute. Yes. And if you do that, you will be directly, after that, you have to apply a measure gate. So just simply apply measure. Ninth is measure. I'm writing all of them together, X0, X1, and X2. They will be getting your value, final value as 0, 1, 1. What I have told you is that how this oracle is actually designed, and then this is something that you have to do for coding. But from this thing, you will not understand that why after oracle and how after applying this Hadamard you are getting your 0, 1. But you don't have to do really any algebraic restructuring and all for quantum. That is automatically done, right? After oracle, it will be designed in that way automatically. So just after this, if you want to see that how what will be the status of your oracle, say I have this thing 000 minus 001 plus 010 plus 011. Say for example 0 minus 111. Then it whatever be the amplitude. So you'll be getting exactly that thing as I told. So this will be an up, this will be down, this will be up, this will be up, this is down, this is down, this is up, this is down. Likewise, some distribution will be watching. After that, whenever you will be applying some Hadamard and all the 3 Hadamards, 3 times, okay, you will be ultimately getting that only for 011 for our example. So it will be some very low probability. They are never exactly 0. So 000, 001, 010, 011 will be high. And then this thing. Likewise, your desired output you will be getting as high. Okay. I think this is clear. Okay. The one who was having any doubt, is it clear now? Screen is not shared, but I was sharing. Okay. Yes. Thank you. Now there will be a bit of like a programming specific constructs. Of course, you have to apply that depending on in what language you are doing it. And by the way, this particular thing is same for all. So what we are doing is how the Oracle works. So Oracle is a program with a specific functionality. Yes. Yes, Gauri. Absolutely. Oracle is a specific term that we use because it's kind of a black box, and there is a story behind it. Should we do this algorithm manually during computing? I haven't got it. Like whatever you want. If you understood the logic, I hope right now all of you have. So in that way only you can do that. Not everywhere you can do. Say I have to convert some decimal to binary. So will we be using some that thing, quantum for that? Never. It's a simple like Python code or the C code, whatever you want to use, you can use that. Okay. And for few logic, say I have to just generate the flag with an A, I have to store. So bitwise XOR. Just consider the example that I have given to you. What question I have given to you? I've given to you that I will be what I have given. It's an example. I've asked you to do it mathematically. So first you do it mathematically, check whether you have understood it properly, then you can go back to your coding. So what I have given is n equals to 4. So only this will be fit as input by the user. That what are the number of qubits that you want. Okay, so there will be some those programming thing that you have to do. The hello world thing. At first you have to ask from user that okay, how many or what is the maybe what is the length of the string. So if they ask you that okay, I want to have a length of the string as say 5, then you have to assume that you have to take n equals to say 5, because the length can be anywhere from 00000 to 111. Or if they maybe give you that I want to like search a secret string within this decimal number, say within decimal 1 2 or within 1 to say 230, for example, I want to search a string. Only this one will be given, and they want to search say a particular thing that will you will ask later. So that means you have to assume that okay, one though I can do with one qubit, and for 230 we have to map that for decimal 230 how many particular qubits you might need to initialize. So further, how you can do that, you just take the binary, convert it to binary, and whatever be the binary value, okay, whatever be the binary value, that particular digit you have to consider, and always take a like seal value for that while considering the number of qubits for that. Okay. For example, if they give you say 30, say 17 is given 1 to 17. So of course, how many qubits you should be using? 5 qubits, because with 4 qubits you cannot, or actually yes, even if they give you 16, because 16 is nothing but 1 4 zeros. So you can use 4 qubits only if the range is 1 to 15. You have to use 5 if it is between 1 to 31. Likewise, you have to just check. I think for this you have to use 8, because 2 to the power 8 is till 255 or 8 ones. So that means you have to take 8 qubits. Initialize all the 8 qubits. But even if you do that, you have to feed all the 0 0 0 0 0 0 0 0 0 till 1 1 1 1 1 1 1 1 as your superposed state. So for our example, if I have given you n equals to 4 and I have asked you to search for this one, which is what? I guess this is your 10. The number 10 is the one that I want to find. So if I give you only n equal to 4 and the decimal number 10, you have to first convert it to binary and have to check this is this one. Then you have to take all these steps. You have to first calculate the how many total number of states should be there. You will be getting it is 16. That means 0 to 15. Then all of these numbers 0 to 15, you have to convert again it to binary, just in order to get this all this 0 0 0 till 1 1 1 1. Okay. And then you can continue with the further steps. So there will be a like bit of those things. We are only here considering the quantum part. Okay. Now, one thing I want to mention that just like here I have said you that it is a -1, so that's why like the phases are either plus or minus. So that immediate click should be there in your mind that that means I might have to use something as a first of all phase shift is there. So definitely phase gate is definitely required. That is the first set of knowledge. Second important knowledge here to consider is that depending on a particular value of a bitwise XOR output, it can be either a 0 or a 1. So it's kind of a control. So how we can manipulate the superposed or individual states of the superposed state? For that, you will be relying on that control. Whenever you have gathered this much of information, then you have to go to your quantum gate library and have to check that which of these gates map maximum to your required task. Of course, I can map it very easily because I have like more experience in that. So I can understand there is a flag here. So that means there is a control and there is a phase. So it will definitely be a control phase. That kind of clicking you need if you want to convert it to code. And for those who are interested in writing the codes for that, we all of us know that we are in the era of ChatGPT. It is already there. Even if you do not want that, just go to Qiskit, draw whatever quantum circuit you have. Automatically, the code will be generated. Okay, so that is there, but you should be of course trying it using your hand first and check whether the logic works for you or not, and then only you can match it that whether it is correct or not. Okay, so this is the thing. I hope now it is clear. And if your logic is say control flipping, say my oracle for a particular problem, I don't know what it is, say for a particular problem, my task is I will be unconditionally flipping it. Then just go for not get. If it is a conditional flip, then go for C not get. If something that just simply I'm swapping the contents of the qubits, then go for the swap get. If it is a multiple control topology, just like the whatever I have shown to you in I was mentioning about a continuous time quanta problem or the binary welded tree, where we have worked on the multi-control topology. So that is depending on your requirement. You have to choose from the quantum gates that what exact gate matches with your task. Okay, I think it is now clear. So I'm keeping it, but please just try to put these two slides in your lecture 4. Okay. So Barnston Wazirni continued. This part we have seen. So next we will be continuing with this thing. So today we will be looking into the Grover's algorithm till the time we have. I think today is the last class, so we'll not wait or waste a minute here. So because there are a lot of mathematics we have to, I will try to show you everything. There are, I think, 4 or 5 different interpretations of Grover. So code is very easy, and there is, I guess, right now a function also available called Grover, but it's kind of a black box. So I'll try to put all the mathematics as much as possible. Don't get confused with multiple interpretations. Some of interpretation are good or easy. Some of them are geometric or bad. But the worst one is the geometric one. But unfortunately, this is the primary and the core part of the Grover essence. If you understand that, you will be understanding entire Grover. I can guarantee that. So searching algorithm is something very basic. Some array will be given to you. You have to, or some linked list will be given to you. You have to find a particular item. So in that way, searching algorithm exactly tells you whether it's a successful or an unsuccessful. And if it is a successful search, it gives you an answer, true or false. And if possible, it returns the position where it had found the particular item within the list. So classical search algorithms are primarily of 2 types. First one is the sequential search, right? It is a linear search. It takes an order of n for n items in the list. Another one is an interval search, or where we actually keep on dividing the array into 2 halves. So the concept is for a binary search, yes, I have this one. So linear search is basically you have a list and you have to start from the index equals to 0. Then these are contiguous allocation, not continuous. Why? Because individually each of these positions you can actually access. So A4 can be accessed, right? That is why we call array as a contiguous allocation. And linked list, on the contrary, is a continuous allocation. Because in order to go to the 4th element in the linked list, you always have to go from the starting element. And you have to keep on increasing your linked list pointer in order to go to the desired position. But here it is a continuous allocation. So likewise, you have to pick up every element of the array and have to check that whether that is your resultant item or not. If it is not, if it is yes, you have to immediately pause. But if it is not, you have to increase the pointer I plus plus or something, then you can again have to check. Okay. And but in worst case, what can happen that you will be again checking the last item and then it is not found. So you will be increasing the pointer by one, and if it is an out of like if the array size is full, we'll be actually going back and tell that it is an unsuccessful search, and it will of course return false. For binary search, the concept is you start with the initial element or whatever is the array given to you. Consideration is it has to be sorted array. So you just calculate the mid first. So mid is your say f plus l first plus last by 2 and take the say floor value. Then you check first that whether the middle item is the correct item that you want to find or not. If it is yes, then you are very lucky. Just return from here only. If it is not, then just check that whether the item that you want to search, that is the item that I want to search, is less than a mid. If that is the thing, then your first will be first only, and your last will be mid minus 1. We all know this, I guess. So, or if this is not true, then definitely, and if middle element is not also equal to item, that means item is definitely your greater than a mid. So now your recursion should work in this way that your first will be mid plus 1 and your last will be last. Or length of the array minus 1. That will be your last. And you keep on doing it until and unless you find your element. So this is a like keeping on dividing the array into exactly equally half. So that is why, so in case of sorting is not done, but normally the complexity of the algorithm is order of log n base 2. But precondition is very important here, that linear search works for any random order, binary search works for only the sorted array. Okay. And if there is no sorting, okay, then considering the asymptotic lower bound theory, we know the best lower bound theory of sorting. We know the best algorithm takes omega of n log n time. So the total complexity will be n log n, omega of n log n plus big O of this log n base 2, which is some part of, I guess, omega of n log n. But considering they are sorted, so it's only order of log n base 2. So why quantum search? Because quantum search is that particular one that can work for any random order, and instead of n, can give you result in order of root n time. Right? Who discovered it? We talked about it. It's a Love Grover in 1996, who was a student of Peter Shor, actually developed a very phenomenal quantum algorithm that can solve it in root n number of time or root n number of queries or evaluations of the function. It can actually find what is the search item, or it can actually find that whether that item is there in the list or not. Okay. So it's called a phone book problem, just like say find the name of the foundation repair service given its phone number. So for with respect to something, you have to find that where it is present. Okay. So the problem statement is something like this. Now from this on, please focus. So the problem statement is that we have a function, say f as 0, 1, 2, 3, likewise till 2 to the power n minus 1. And this one particular item as marked as pink is the target item that I want to find. Okay. And your algorithm, linear search, would take it order of n time to find this one. Say w is the one that you want to find, and k is its respective position where your w resides. So this particular thing can be done by Grover in order of root n number of queries. Right? So on that note, let us go back So we will be doing all the calculations, and then we will try to map that what was the two things. Before getting directly into this, in last 5 minutes, we will go through this one. So let me start. You will be understanding it, no issue. So we will be starting with Grover. I hope you got that initial like part from where or what is our context. So let us start with Growers. So let our capital N is equals to 2 to the power n. That is our total number of data is basically should be less than or equal to n. Number of data. You must be understanding it. Why? Because accordingly we have to manipulate the number of qubits, which is small n, such that your n is your number of qubits. Easy. That means for 8 data, 8 is less than equal to 8. Number of inputs is number of qubits is 3. And if it is say 18 data, then 18 should be less than equal to 32. That means your n should be equals to 5. Clear? So accordingly, so that our input is an n qubit data. So we have an oracle which defines the needle in a haystack function. Okay, so which is can be defined as or defined over k such that this is true, this is true such that f of k is equals to 0 for all k, for all k where k is not equals to w. W is the one that I want to search. So this is the item, say, or the I mean the successful one where your data is present or whatever index you want to search. And f of k will be equals to 1 for k is equals to w. So k is all of those values starting from 0 to 7, and for all the values f of 0, 1, 2, say I want to find w equals to 4. So except for f of 4, f of 0, f of 1, f of 2, 3, 5, 6, 7, there will be 0. For only for k equals to 4 or w equal to 4, f of 4 will be equals to 1. Okay. So now your Grover oracle will look something like that. For your Grover, your oracle will look something like, oracle is very simple initially, or this. So this is your unitary f of w, say, because w is a 1, so that's why I have written here w, and y is this one. So this is your input, and this one is your target. So your input will be unchanged, and your target will be y XOR f of x. This is your target. So from Deutsch, Doxa, Deutsch, Bartz and Vasilini were actually looking. This is a very generic oracle structure. Okay, and how to define your U for Grover, that is a big challenge that we will look into. Give me a second. Okay. So Now f of wx is equals to 0 where x is not equals to w and 1 for x equals to w. So on that note, say if my y is equals to ket0 minus ket1 by root 2. Now you might ask me that how we can define this one. Y is your target, so you can realize it because if you have initially 0 and if you fed it to an x gate, it will become, or not gate, it will become 1. Then if you apply a Hadamard gate, it will become ket0 minus ket1 by root 2. So all these two gates, x and x, you have to put in terms of y when you will be implementing it for code purpose and all. But your target register will ultimately be y. This is a symbolic one, and x and h is the actual ones that you use. So whatever be the target, accordingly you have to do that initial calculations and have to put it. So if your target register y is this thing, that means your output will be -1 to the power fwx, then get x tensor y. So instead of y, it will be 0 minus 1 by root over of 2. Right? And this particular thing is basically that target is equals to y XOR fwx because it's y XOR fx. So if y is equals to 0, it will be fwx. And if y equals to 1, it will be basically fw bar x. Right? We know that 1 XOR x is x bar and 0 XOR x is x. So that means 0 XOR fwx is fwx and 1 XOR fwx is fw bar x. So this thing I can also write in this way, right? That -1 to the power fwx time fx. Remember why we are doing all these things, or how Grover has thought about this is because he simply wanted to introduce the quantum amplitude amplification. So for which some sort of phase inversion logic he want to bring into picture. So how we can bring the phase? Just like we have seen in case of that Weinstein Vazirani example, in order to bring the phase, you need something like y -1 to the power something, where that fx is the flag. Clear? So there is a control z kind of thing. So this is -1 to the power this thing. Now, see, this is the first register, this is the second register. How I can claim that? Because it is not commutative. So definitely that means in output, the first half before the tensor is the first register, second one is the second register. So the second register, therefore, you can see one thing, the second register is unaltered, but I'm trying to write everything so that later on, whenever you will be revising it or again doing it, redoing it multiple times, you can actually figure out that why and all those subsequent steps. But the first register has a phase, has a phase, depending on fwx. That is my flag. So if fwx is 1, the sign of first register is flipped. And if fwx is 0, of course it is unchanged. Now a quick recap. When fwx will be equals to 1? Whenever your k is equals to w. That means we can understand one thing, that from the initial Grover oracle, what we are aiming towards is, say if 101 is the item that I want to find here, right? That means only for 101 there will be a -101, and for the rest of the values, because only for this fwx will be equals to 1. So this will be minus and all of them will be in plus direction. Something like that. Let us see, like this is all of these things we will be keeping on interpreting or understanding. So alternatively, therefore your output is minus 1 to the power fwx x into 0 minus 1 by root 2. So if two things are there, as we mentioned, if fwx is equals to 0, it is it x into this thing, right? And if fwx is equals to 1, it will be minus x into 0 minus 1 by root over of 2. Okay. So the first task, or we actually what we have done is for the marked item or our desired target item, we actually have done something. We have somehow started with identifying it and by inverting the phase. But only by this can we do anything? Nothing. Because whenever the phase, though the phase is there, unless and until whenever if we measure it, that we will not be getting anything because of the phase. So we have to somehow tell my quantum system in a way that you have to come up or emerge with something which has a very big probability than the rest of the values. So it's in the play or the game here is in terms of the amplitude, not in terms of the phase. Clear? So that means now let us define the first oracle operator officially. So define an unitary operator. Say UW for the marked item, it is W, which is I identity minus 2 W and W. And why we are doing this thing or how this suddenly this thing have came when this UW acts on W. How this is coming? Because if it is applied, then UW on W, that is this operator working on the marked state W, is nothing but, so W, this means this is W minus 2. Let's check. This is something because I minus this entire thing times W. So which will I into KW is KW minus this is 2 into KW. This was bra W, so this is this entire thing. Now we know that this is nothing but the inner product of the same things. Inner product of two same term is nothing but what? 1. Because they are always orthogonal to each other. So their inner product will be 1. So that means this is W minus 2 KW. So 1 or x minus 2x is nothing but minus x. So this is minus W. So that means your UW of W has make it minus W. Now, what we will do? Now we will take a linear combination of computational basis of all of our inputs. This is one, just like see, once you do that, this is a benefit for quantum. That is a quantum parallelism, everything we can do, quantum offers superposition. But this is a challenge as well. Whenever the ones who are working on the quantum algorithms, this is very challenging because quantum only understands that picture of superposition. It can only behave as superposition. So only if you give a pure state to quantum, this is equivalently putting a pure state to classical. When you can leverage the power of quantum, if you are doing something whenever it is in superposition, but it is okay, it is theoretic definition. But if you are whenever you are implementing it, you have to encode it in a way so that it can actually give you some benefits rather than having all these challenges. Okay, see, linear search, this is so easy. Just traverse the array. But here, though we have identified it, though we have phase inverted it, but it is in the oracle state. There is no such something that is coming out to you. You are checking it, you are understanding that it can make it. But this is not true for quantum. So quantum itself has to come out of its quantum world and give you, by understanding that, okay, so this is something that I think I'm more biased about. That is the amplitude amplification. Only after that you can measure it. Okay. So if we do that, say our linear combination, say this uniform combination or linear combination is, say, S as the standard state or superposed state, whatever you say. And your S is nothing but 1 by root n. This is the superposed one. We are keeping on writing this. X equals to n to 0 to 2 to the power small n minus 1, or equivalently capital N minus 1. Because 2 to the power small n is equals to capital N. So what is this X? This is collection of all states in computation basis. This is the collection of all states in your computational basis. Means all the 0, 0, 0 and all. And by definition, this is very important, note, by definition, since KW is a member of S, then this inner product of WS should be equals to 1 by root over of N. Okay. Let me give you a small example. Say why this is true. That is a proof of one. Let me just mark it at equation, say 1. Let me have a proof for equation 1. Say with a very small example you will understand. Say n equals to 2 qubit. Then capital N will be 4. So that means your S is nothing but 1 by root over of 4. That is half 800, 01, 10 and 1. And say your W is, say, 10. So what we want my WS should be 1 by 2. So let us see whether that is true or not. So WS will be, what is your W? 10. That is, this one is bra W, that is this thing. Product, what is your S? Half into this entire thing. That means it is half. Just take it as common. Then it will be 1000 plus 1001 plus 1010 plus 1011. Now you know all these things will get cancelled out because they are just the inner product of two not similar item is basically 0. Okay, I don't think I have to prove this one as well. You can check it by yourself. Inner product of 0, 0 is 1, but inner product of 0, 1 is 0. So similarly, inner product of 1, 0, 1, 0 is 1, but inner product of 1, 0, 1, 1 or any other state than 1, 0 will be equals to 0. So this is nothing but half into all three zeros, and this one is 1. So this is half into 1, that is half, which is exactly equals to 1 by root over of 4, and we started with 4 states. Clear? So we will be incrementally proving each and every individual steps for Grover. Okay. Now the next one that we have is this thing. So this is the first operator. First operator, UW. Where is it? Yes, UW. Now we will head towards the second operator. Yes. So the second operator is, so Grover defined another operator, US, such that US is equals to 2 get S draw S minus I. Now you know what is your S. This is your that standard superposed state. And this US is called a reflection operator. So suppose we let US to work on arbitrary state psi, then since any state psi can be resolved, this is all happening in quantum paradigm. Remember, this is not classical, and these are all photons. So that is why reflection properties will definitely be there. So any particular state or some say photon ray or psi can be resolved into components or component. One is along, that is parallel to the standard state, and this, okay, so that is psi parallel, and second is along perpendicular to the standard state is such that it is psi perpendicular. So meaning psi is nothing but, or it can be written as psi parallel plus psi perpendicular. Then if this US or the reflection operator acts on psi, then the component which is perpendicular to S remains unchanged, right? But the sign of state of say state perpendicular will to S will change its sign, because outer product of get S bra S will be equals to 0. So after these two operator, there is another operator, third operator from Grover. So the last and the third operator, or the final Grover operator, which is also known as rotation operator, also known as, or RG, also known as Grover rotation operator, or RG, can be written as, first you have to apply UW, then you have to apply US. So this, the precedence is from right to left. because this is an operator also. So it will be applied on some state. Right? So this is first you have to do, this is the second one. And this total in this sequence is known as the rotation or Grover rotational operator. Right? So that means on application of, first you have to apply UW, then you have to apply US, then you have to apply RG, and all of them together is known as the Grover algorithm, or their application is known as Grover's algorithm. Now, when we apply, say, I'm just writing, instead of writing everything, I'm writing in this way. So whenever we apply UW on psi, it will make it psi 1. Okay. And then say 2 is, if we apply US on psi 1, then say we are getting psi 2. Right? Whatever, what was my psi, I don't know, but initially its psi will be, initial psi will be psi 1, and then it will be on psi 2 on application of UW and then US. Okay. So now we will be going into that geometric interpretation. So I will be using it in the second page. Remember, W is the marked item. So this is something that I want to find. And your S is the superposed state or the standard state. Okay. Now, say the geometric interpretation of quantum. Say the geometric interpretation of quantum rotation or group. Focus very carefully. Okay. So say in the xy plane, here you have your W. Okay. So that means this one is the W perpendicular. And similarly, this one also W perpendicular. Say this is your S. Your S is in this place. So this is your ket S, which is a state of or set of superposed states. So this is your psi, where you have your arbitrary initial quantum state. Let me assume that the angle made by this is theta. Okay. So if that case, what will be this angle? Because this is pi by 2, so this will be pi by 2 minus theta. And say that angle made by W and this psi is the your phi. So similar to W has a WL, that are perpendicular component, S also should be having some perpendicular component, right? So it's a bit difficult to draw. It will be somewhere like that. Just assume that this is the perpendicular. I hope it is more or less perpendicular. Okay, so it is perpendicular to S. So that means this is your S perpendicular. And similarly, this one is also your S perpendicular line. Right? So, but if this is your theta, then this one will be your the cos component of S. So this is your S cos theta. So in that case, the remaining one, this part will be your S sin theta. The pi by 2 minus theta part, that is your S sin theta. Okay. Now, say now on application of your US, on application of US. So one means, sorry, not the US, the UW. This is application of UW on your site. This is what I am marking as 1. So on application of UW on psi, it will actually go to psi 1, right? So it will be going to your psi 1. And this is something like that. Say, here it is. So this is your psi 1. So that means if this is phi, this angle will be phi. And say this angle made is lambda. So that means if this is lambda, okay, then, okay, first of all, this is an application of UW. On psi, I have got psi 1 here. And say now this angle made by psi 1 and perpendicular of S is lambda. Now if this is S, so this one will also be S. That means just like this is W. Okay, so this is also W. And it will be unchanged. So this is also S. And now say an application of US, that is the second operator, on application of US on psi 1. Okay, you are somewhere here. So this is, say, my psi 2. And this one you have got on application of the second one. Okay, so this is on US reflection operator. And say this angle, if it is lambda, so definitely this angle will also be lambda, vertically opposite angle. And in that case, this one will be, if you just calculate, this one will be your theta. And also by like pi and minus this and all, if you check, this is also same as pi plus lambda. So let me just write it. Okay, just a minute. Okay, yes. So let me just write it down. So the angle between KW and perpendicular of S, or the superposed one, is theta. And this is equals to the angle between S and perpendicular of W. So this is also theta, and which is equals to phi plus lambda. And the second is the angle of rotation, say angle of rotation between psi, which is the initial one, and what is the final state? Psi 2. Psi to psi 1 to psi 2. So psi and psi 2 is what? Is basically, I'm just writing it here, otherwise. So this is nothing but your phi plus theta plus lambda. What it is? Phi plus theta plus lambda. This is your, this one. So this is your initial one, and this is your final one. So it is phi plus theta plus lambda. So which is nothing but theta is equals to 5 plus lambda. So it's 5 plus 5 plus lambda, or say 2 5 plus lambda, or equivalently we can write it 2 theta. So why I am writing only 2 theta? Because initially we are starting with the superposed state, and from the superposed state we are starting to convert. So instead of writing it in terms of phi or something, mark state we initially do not know, so how we can get the excess of phi? So considering all those things, we are starting or actually picking the angle theta, which the superposed state initially starts with. And what is the target? See, this is the entire picture. We will get into the details of it as well, because and why this thing is very important. Otherwise we cannot proceed further with the like thought process of Grover, that how he designed it. So the mathematically there are a few like matrix form of it, but and all those things are there, but all the notions, all the remaining notions are primarily based on the ge- geometric version. And the angle, that 2 theta, this is very important, and there are no further interpretation that can lead to this out understanding that one rotation, one Grover or one RG, which is UW, US, and all those things, can make an angle shifting of 2 theta. So the concept of angle, if we have to understand that, this is the notion behind the how many iterations we need and why the complexity of Grover is order of root n. We cannot get into that. So for that, we need to understand that why in one rotation where there are two different operators involved, first is UW, second is US. That is, first is the phase split, second is the reflection. My angle of rotation will be 2 theta in one rotation. Okay. So in order to understand this, we actually have started with this particular geometric one. So therefore, a few observations, a few theoretical observations, what we have got is that, so therefore, after one such entire Grover reflection operator, or say rotation, the angle between initial and final quantum state is 2 theta. This is what our observation is. Now there is a question. Say the initial superposed set of states, say for example, contain 100 states. 100 states. So it's a 7 qubit, some sort of thing. And out of which 99 states are not definitely the desirable one, right? Say I want to find the state with the decimal value, say 94. That means all the remaining values, they are not required. So in that case, but on and only one state, so 99 are gibberish states and only one is my ideal states, and we are starting with all the 100 states. Okay, so what my target, what is my objective for Grover is that how we can converge from the state of 100 states to the desired one state. Like, so what is our objective? Our primary objective is how from a set of, say, superposed state or S, set of S, we can slowly converge to W, which is the desired state. How we can do that? And since you know that Grover is nothing but these, like from the start state, we are just keeping on rotating it. So, like two operators, we are keeping on rotating, say. So, after how many iterations? Because if we do not stop, so either it will be a some infinite loop, and we will keeping on doing that. So, does it mean that if we keep on increase the rotation number, will my algorithm very fast converge to the earlier state? The answer is no. Why? Just you imagine the diagram, say psi, psi1, psi2. Then again some psi, psi1, psi2. Again from psi, psi1, psi2. So in second round, your psi 2 will be psi, right? The final state of the first round will be the initial state of the second round. Similarly, the final stage of the second round will be the initial state of the third round. So if you keep on doing that, maybe every time you will be somewhere closer or a distant position than W. But where you should actually stop? What you want that ultimately by keeping on rotating, you should stop exactly at W. So W is your some item where you want to stop through these rotation operators. So definitely one thing is confirmed that it cannot be an infinite rotations, because if we keep on doing that, maybe we were very close, maybe 10-degree closer to W, but unfortunately we made another rotation and we again have shifted to some more angle gap. There is a more lapse in terms of the angle between the that particular psi final and W. So again it is lost. So there will be a lot number of unnecessary rotations. So that means, so the first arbitrary state psi resolved into your this and this. Okay. Therefore, your psi is equals to psi parallel plus psi perpendicular, and the angle between S and WL or W perpendicular is basically theta, and angle between S and W is your pi by 2 minus theta. So this is a thing. Now say we have a 4 input data. We have a 4 input data. That means my n is equals to 4 and number of qubit is 2. Then what will happen? The initial angle between my S and W is what? Is basically your cos pi by 2 minus theta. Right? Just in the diagram you have seen that. If this is S cos theta, this is basically S sin theta, which is cos 1 per pi by 2 minus theta. So let me say it as phi dash, or yes, sorry, theta dash. So it is basically cos theta dash is the thing. Cos theta dash is nothing but S. How we can calculate this one? This one divided by this and this. That is how we calculate it. So if you calculate it, it is basically half times root over of half square plus half square likewise. So it's 4. That is, it is half divided by, basically this is 4 into 1 by 4, that is 1. So it's half. So therefore, your theta bar will be cos inverse of half, which is cos 60 is half. So it is basically 60 degree. Right? Therefore, your theta bar is equals to 60 degree. Therefore, your theta is nothing but pi by 2 minus theta bar, because theta bar is pi by 2 minus theta. So that is 30 degree. Therefore, a single rotation will rotate it by 2 theta, that is 2 into 30 equal to 60 degree. And what was our objective? To align S to W. So the gap is basically 60 degree. Now say cos inverse. Say now in the second iteration, you have some theta, might be having some theta as, say theta bar, in the similar formula we'll be getting maybe say cos inverse of 1 by root 8, considering n equal to 8 1. Then it will be, it's approximately 69.29 or 70 degree, let me say. Okay, so that means your theta will be 20 degree approximately, 90 minus 70. So a single rotation might increase it by 2 theta, that is 40 degree. So often by keeping on rotating, we might exceed the mark state. So this will increase the rotation. Okay, because if it is only 60 degree, we only needed the remaining angle, but it again has shifted it. So again, we actually have come below W instead of converge. Okay. Now, so here we are actually left with a very important question, that is optimally, how many number of rotations are needed Okay, now we will converge to this one, but we will see another interpretation. After that, we will be actually answering it because both are required in order to get this one. So first, one single rotation takes how much angle? 2 theta angle. And what is theta? The angle made by S and the perpendicular state of the mark state. Do we know what is the mark state? No. But the angle made is theta. Now the second question is, how many number of rotations are needed? So the geometric interpretation is over. Now we will enter into another interpretation. So that is, now say your psi is sigma x, xx. Okay. And your S is 1 by root n, x equals to 0 to n minus 1 times x. Therefore, S inner product psi will be nothing but 1 by root n. Then this is x, and say this one is x, and say one is x bar, because both are the same variable. So it's nothing but, it's not x into x bar, it's the same thing, x or x bar. Then ax, then x and x bar. The psi I'm just taking x bar because both are same variable. That is why I'm writing this thing. So this is 1 by root n, because this is same. We know the inner product of same is basically the same variables at 1. So this is 1 basically. So this is ax into 1, which is nothing but ax. This is x equal to 0 to n minus 1. So this is 1 by root n times ax, x equals to 0 to n minus 1. Now, what is the mean amplitude? Now the mean amplitude will be, I forgot to mention, sorry, ax is the amplitude. Right? So what will be the mean amplitude? Mean amplitude is the mean, means the average amplitude. So it's a bar equals to sigma ax, summation of all the amplitudes divided by the total number of states. Okay. Now, S and psi, their inner product is nothing but 1 by root n times this ax for x. So this is, if I just want to write, that means from this equation I can write that sigma ax is nothing but n into a bar. So that means I can write this is n by root n into a bar. So this is root over n into a bar. Okay. So therefore, alternatively, in terms of the mean amplitude, we can write this is root A into A bar. Now say US is working on psi. That is, a reflection operator is working on psi. What was the definition of the reflection operator? This one. This is 2 get S bra S minus I. This is being applied on get psi. Now this is 2, this one. We can write this thing and this thing together minus this side. What is this value? Root n into A bar. This is 2S root n A bar minus psi. Now this is nothing but 2 root n. Now get S is nothing but 1 by, okay, let me write A bar as well. And this root S is nothing but 1 by root n into sigma x x. And this is my psi. So they will be cancelled out. So this is 2A bar into sigma xx. And psi can also be written as axx. So sigma we can take together and we can write it as sigma x 2A bar minus ax times get x. This is another sub part that we have seen. So now we will understand that what it will do whenever we will apply it on some arbitrary state. This is the operator formula, right? 2A bar minus ax on x. So that now we will look into the interpretation of application of our US on psi. What it was? US on psi was sigma x 2A bar minus ax times get psi. Sorry, get x. So before US is applied, before this US operator is applied, what was my amplitude? Amplitude of x. Amplitude of x in psi was only ax, right? And after US is applied, the amplitude of x in psi is 2A bar minus ax. We can see that initially it was only ax times get x. Now it is 2A bar minus ax times get x. Now, measuring both amplitudes, that is before and after, measuring both the amplitudes with respect to mean. What is your mean? A bar. So if we do that, therefore, the amplitude with respect to mean is, for initial amplitude, it is ax minus a bar. This was your initial, this is your final. And amplitude with respect to mean for final is your 2A bar minus ax this thing. So this was the thing, 2A bar minus ax. So this is minus a bar. So that is your a bar minus ax. Now ax is nothing but a bar plus minus delta. Okay, delta is a very small change. So your this thing will be so if I just want to write, this will be So your 2a bar, just a minute, your 2a bar minus ax will be, alternatively I am writing 2a bar, let me just get here. So it's 2a bar, ax is nothing but a bar plus minus delta. So 2a bar minus ax is, we can write it as 2a bar minus a bar plus minus delta. So this is a bar, this is minus plus, okay, or 2a bar minus a bar, this is minus plus delta, that is a bar minus plus delta, or it is like minus a bar plus minus delta, which is nothing but minus ax. This is the same thing. Just considering, we can write ax as a bar plus minus delta. Okay, so now your initial amplitude or your final amplitude has undergone inversion about mean. Mean means the mean amplitude. So that means there are two phases here also, you can understand. The first one is phase inversion, and the second one, this is not with respect to phase, okay, this is about amplitude. So second is inversion about the mean. Now let us understand with respect to let me start here only. Say an example, whatever you have learned, we will have a quick check of that. Say my n is 8, that is my number of states is 8. And Oracle, after application, has already knowledge. The Oracle, after application of FWX, that is, we are starting with something, nothing else, has already knowledge. There is a phase inversion is done. That is the meaning. Already knowledge of the mark state. And what is that state? Say that is W is equals to 4. That is a mark state. That means W, KW is nothing but 100. That is the set. So let us see how this inversion about the mean, or how it is actually relevant with respect to Grover. So in S is your standard superposed state. Each state has amplitude of what? Has amplitude of what it is? 1 by root n. That is 1 by root over of 8. Therefore, because your n is 8. So therefore, after UW, amplitude of W is what? Minus 1 by root 8, because the phase inversion is done. W is for phase inversion. And amplitude of say some U, where U belong to S, but U is not exactly equal to W. So for those cases, it is no phase inversion. That means plus 1 by root 8. So therefore, your mean amplitude A bar will be what? Meaning amplitude will be what? 1 by 8, 0. This is for 0, this is for 1, this is for 2, this is for 3, this is for 4, this is for 5, then 6, then 7, divided by how many states? 8. So this is nothing but your one of these values will get cancelled out, so remaining 6 values will be there. So this is 1 by 8 into 6 by root 8. So this is nothing but say 3 by something, what it will be? I guess 8 root 2 or something. Okay, and this is basically 3 by 4, so 4 is again 2, so some of the 2's will get adjusted accordingly. So in terms of root 2, it is 3 by 8 root 2, or you can also write 6 by 8 root 8, no issue. Okay, now you W is there, and this is the status. This is the status of the mean amplitude. Therefore, our application of US, you have to do. So, amplitude of all states, or a new amplitude of all unmarked state, that is U, unmarked state. Say that will be 2a bar minus ax. So that is your 1 by, just you calculate it, it will be 1 by 4 root 2. Your a bar is 3 by 8 root 2, and your ax was, initial amplitude was, for all of them, 1 by root 8. So it's 3 by 8 root 2 minus, like 2 into 3 by 8 root 2 minus 1 by root 8, it will be 1 by 4 root 2. And for the marked state, W, it is again 2 into 3 by 8 root 2 minus of 1 by root 8. So here you can see that unfortunately its amplitude, instead of getting diminished, though it's before this US it was minus, right now it will become very big and it will become 5 by 4 root 2. Okay, therefore amplitude of the marked is basically, or say W, here you are getting as 5 times the amplitude of the unmarked, or U. That also means that therefore the probability, the measurable probability of the marked one, since probability is nothing but the square of the probabilistic amplitude, so it's 5 square into probability of the unmarked. So this is, the probability has increased 25 times. And this particular phenomena is what we were talking about, discovered by Grover, known as QAA, or quantum, because it's a quantum algorithm, then amplitude, you're increasing the probabilistic amplitude, and amplification, or our very famous second paradigm called QAA, right? This is a major milestone that had been observed. Now, now say, yeah, very good. Say I need m number of iterations. Remember, this is where only, this was the only one thing that we were left with, that how many optimal number of iterations are required. So say I need m number of iterations to bridge the gap between, my S and W, superposed to the marked one. I want to convert. So one rotation makes an angle of 2 theta. So m rotations should be, or iterations should make an angle of m into 2 theta, right? So this m into 2 theta, finally, let me go back. This m into 2 theta should match the gap between S and W, which is pi by 2 minus theta. This is all that I want, right? So m into 2 theta ultimately should be having exactly the same angle gap as pi by 2 minus theta. So that means there we can frame a very straightforward equation, that is my m into 2 theta is nothing but pi by 2 minus theta. Calculate. So m is 1 by 2 theta, it will be here, into it is pi minus 2 theta by 2, which is pi by 4 theta minus half. So which is, this is your m, right? So you can write it down in this way, that m is pi by 4 into 1 by theta minus half. Now we know that this sine theta is basically your sine theta and the cos theta. That equation, if you remember, that cos theta was, it's cos theta bar, because, okay, let me write it. Cos theta bar was equals to, what was that value? It was equals to your, I guess we computed that value. So it was, I think 1 by root n kind of thing. And sine theta is nothing but, okay, or alternatively, let me write. So cos, this was pi by 2 minus theta, that was 1 by root n. And we already have seen why this is true. So this is nothing but sine theta, which is equals to 1 by root n. From this particular thing, from very easy, sine theta plus cos theta equal to pi by 2, we have this thing. Now what is the value of sine theta? Very sine expansion, series expansion, it is basically something like theta minus theta cube by 3 factorial plus theta to the power 5 by 5 factorial, something like that, and so on up to infinity. Now considering the higher order terms, considering the higher order terms to ignore or to be ignored, we can get one thing, that is sine theta is equals to theta for theta very small, right? Or higher order values having very less impact on theta. So that means sine theta is equals to theta. So by that thing, can I write that theta is nothing but 1 by root n, because sine theta was equals to 1 by root n? Can we write that? Definitely yes. So from this, now if you want to substitute this thing in this place, so what you will be getting? We'll be getting m is equals to pi by 4 into 1 by theta, which is root over of n, minus half. Now half is a constant, pi by 4 is nothing but 45 degrees a constant. So that means that number of iterations required is a factor of order of root n. And this is the most well-known proof for complexity for Grover, that in maximum root over of n number of queries, where here query is not a simple query, it's iterations. So that means in terms of root over of n number of iterations, you can actually converge in quadratic speed up the marked item. And why it is marked item, or why it is related to m? Because check, we actually have collapsed these two terms in the LHS and RHS. That means it has to merge or converge. And whenever we are converging, there only the W's amplitude will be amplified. And we have seen through this example where we have seen the 25 times the probability is getting amplified, because 5 times the amplitude is getting amplified. So here is where I want to pause today or end today. Only one thing I want to show, that is the relation between theta and n. There is another relation, and the matrix form as well. Okay, these two things are not going to take much time, maybe 10 or 15 minutes max. So tomorrow we will be starting with this particular thing. Let me first save it. Yes, so I'm stopping sharing. Yes, so whatever question you have, screen share. Okay, there was some issue. Okay. Okay.
Yes,
There's
ma'am.
some questions in between. Right now, is it all clear?
Yeah, participants, if you have any doubts, you can ask. Some questions were there, ma'am. Any book you can refer for Grover algorithm? One question.
For Grover itself, you can refer Grover's paper. What else?
Please refer to the paper, research paper by Grover. So you can look at Grover's algorithm.
Yes. Yes. Okay.
That paper. इधर इधर देख के.
Okay. Anything else?
Yeah, I
This
think
is
so.
very difficult algorithm, and another very difficult one is short. Still, I think 10 or 15 minutes more is required. We can skip that if needed, but for a completion, if we want, we can do that if needed.
Yeah, ma'am. If you, yeah, ma'am, if you want to continue, yeah, I think that's not a problem. Participants, is it okay for you
No,
for
not today, sir.
clarity?
I will be
Not tomorrow.
continuing it tomorrow,
Yeah,
I guess.
tomorrow. Yeah, fine. That you can plan, ma'am. Ma'am,
Yes.
you have two more lectures to go ahead, right? So that is tomorrow's lecture is there. That is September 4th. Uh, Quantum communication you will be starting, right? And
Yes.
you will be completing quantum communication on September 6th. Fifth is a holiday, ma'am, Miladun Nabi. Participant, please note, Miladun Nabi will be holiday on September 5th. It's a public holiday. MNIT is also holiday. So please, we will not have any class. You please prepare well for your exam. The syllabus will be tomorrow's class, till tomorrow's class, whatever madam teaches. So today's slides are being circulated. So the slides will be with you. Please prepare. Ma'am, you can share the slides now itself so that we
Yes.
will pass it to the participants. It will be available in your Canvas files. Please note the slides, handwritten, wonderful material. It is there. You can follow the video. Along with that, you can keep the slides and go through. You will understand very clearly. These are difficult concepts, but we are just giving you a overview. Again, we will discuss these topics in QT-04, right? So please note these points. So don't worry if you're not understanding, it will take some time to digest. So that's why we will repeat these concepts. We're just giving you an overview now. Please try to understand that, right? And then slowly we will take it forward. And we are completing quantum computing now. We are going to quantum communication from tomorrow onwards. Professor Anil Prabhakar was supposed to join tomorrow, but he will be taking the lecture on September 11th. He has promised, and Dr. L. Venkata Subramaniam will also be there from IBM. Both of them will take 1 hour each. And so September 11th will be a wonderful day for us. Two wonderful experts, one from academia and one from industry. Both are leaders in quantum communication and quantum computing. If you put it, Dr. L. Venkat Subramaniam is the leader, India quantum leader from IBM. And Professor Anil Prabhakar is the quantum communication leader from the academia side. He's from IIT Madras, so he's very much associated with this training program. He's our mentor while running this program. When we put the schedule and all, he approved it. So we are looking at that, and he is guiding us. So he will be there sharing the communication aspects, but the lectures will be covered by Ms. Nivedita herself. So 2 days, she will discuss quantum communication introduction. She is taking quantum communication lectures in the QT-06, a full course that is there. Those experiences also there. She has already taught quantum communication earlier also. Then we'll have Ashwat Babu sir coming back from 8th, 9th, 10th. 3 days, he'll be talking on quantum sensing and materials. He'll just introduce the quantum sensing. So all the four verticals: quantum computing, quantum communication, quantum sensing, and metrology, that is actually, but we are discussing only quantum sensing, quantum materials and devices, but we'll be discussing quantum materials only. So that will be the introduction to quantum computing is what we'll cover. Then we'll go back and again start from fundamentals, which is called, the course is called Foundations of Quantum Computing, Quantum Technologies, Foundations of Quantum Technologies, FQT. That is the course. QT-02 will be starting after this. 1 week break will be there. So you will just get time to refresh yourself. Then again, You will be starting from 3 o'clock, 5 o'clock will be starting. Most of the speakers will be there, and new speakers will also be available. So we'll take it forward. If there are no doubts, okay, yeah, no problem for attendance and all. Okay, network problem, no problem. Okay, okay. That's okay. Please listen to the lectures in Canvas. Log in through WebEx using your registered mail ID and the password that is given. We will consider your attendance. So please attend it forward. We will give the attendance sample once few more days are over. We will give you what is the attendance on the Canvas that you have observed, whatever videos you watched apart from the time. We will give you that, right? Yes, as of now, we'll keep these recordings available after the completion of course. They will be available on YouTube, like how QT-01 is available. These videos will also be available as part of QT-0001 series of AP Shea. So that videos will be available. So don't worry, it will be available in YouTube. But of course, we will make them available for downloads before we wind up the course, right? Once we are winding up the course, we'll give you some time. You can download these videos. As of now, they are not downloadable because you will say that, sir, we downloaded and watched the videos. We don't want to consider that. So we please understand that this is not permitted. So presently, download is not permitted. But once the course is over, you can download the videos. They will be available on YouTube also. You can download the videos from there as well. Right. So all the best. Thank you so much. So we'll meet tomorrow at 3 o'clock. Then we'll take a break on September 5th. Then on September 6th, we'll conclude with Nivedita madam completing quantum communication. Thank you, ma'am. Thank you, all participants. We will stop here.
Thank you so much, sir. Thank you, everyone.
Yes, ma'am. Send the slides. Yeah.
Sure, sir.